So now we're going to look at the effect that intermolecular forces have on solubility of substances. And so again, we're still worried about how those molecules are interacting with one another. Not only how the molecules, like in a solvent, are interacting with one another, but how are they interacting with the component that we're adding. And that's where we're going to get this idea of solubility and trying to predict what substances are soluble in others. So let's look at two examples here. We have ethylene glycol and motor oil in water. And what we look at with ethylene glycol is we have this two carbons here. Okay, so that's where the eth part comes in there. So we have two carbons there, and we have two OH groups. Now we know from our definition of hydrogen bonding that these hydrogens will undergo hydrogen bonding because we have a hydrogen attached to a fluorine, oxygen, or nitrogen. We actually have two sources of that. And what we'll see is that these hydrogens are going to interact with the oxygens on the water molecules, and the hydrogens on the water molecules will interact with these oxygen atoms. And so we see lots of similarities in their intermolecular forces between water and ethylene glycol. And as a result, ethylene glycol will dissolve in water. And so ethylene glycol is actually the antifreeze in your car because it lowers the freezing point as we add it. And so we don't want our car to freeze, or more importantly, in the summer, we don't want our radiator to overheat. It also raises the boiling point. We won't really get into those properties as much. We'll talk a little bit about it briefly in the next chapter. But we see that we have similar intermolecular forces here between ethylene glycol and water. When I look at motor oil, remember I'm dealing with these long chains of carbons, these hydrocarbons, these alkanes, and all I really have in this is dispersion forces. I've got no polarity, so I have no dipole-dipole forces, no hydrogen bonding. And what happens is they don't want to hang out with one another. The motor oil, these alkanes, would rather hang out with other alkanes because they have similar intermolecular forces. And when we look at the water molecules, they have the same intermolecular forces, so they want to hang out with each other. But we don't see any mixing occur. We don't see that oil dissolving in the water or mixing with the water, simply because they have very different intermolecular forces. And if you've ever looked at, say, oil and vinegar dressing, what you see is that the layers will separate from one another. And so you get the oil layer and you get the water layer as well. So we can look at sugar, and we see that sugar dissolves in water. So here's our sucrose. This is just table sugar. And what we see is that we have some oxygens and hydrogens here. So we have an oxygen that can undergo hydrogen bonding here because we have a hydrogen attached to an oxygen. Here we have this oxygen available for hydrogen bonding to the water molecule. And we're just showing a few of these spots where we can actually see hydrogen bonding. There can be others. This one can be involved, as can this one. But what we see is that there are ways for the water to interact with that sucrose molecule because they have similar intramolecular forces. They have that hydrogen bonding and they're going to mix. Now, it's not just hydrogen bonding that results in something dissolving in another substance, so dissolving in a solvent. Sometimes they both have dispersion forces. Sometimes they're both polar, and so we can have lots of different combinations. Now, polar substances, because water is also polar, will dissolve in water. The big difference is between our nonpolar, which just have dispersion forces, versus the polar substances, which have polar molecules and polar bonds, polar intermolecular forces, as well as those dispersion forces. But remember, in a polar molecule, those dipole-dipole forces are much stronger than those dispersion forces. So let's look at some examples and see which of these is going to be soluble in water. Now we see sodium chloride is table salt. That's an ionic compound. And so what we're going to see is that will be soluble in water. And we saw this when we looked at the ion dipole forces. We actually saw those water molecules kind of surrounding those ions because they broke apart from one another. And so we see that we've got the water molecules surrounding each of these ions. So it surrounds the sodium ion and the chloride ion as well. Now, when we look at sucrose, we see it's a polar covalent molecule. So we know it's polar. We saw that on the previous slide. And it's covalent because we're dealing with covalent bonds. They're sharing electrons. And this too is also soluble in water. Now, when I get to vegetable oil, I see that it is a non-polar compound. And as such, it doesn't have that polarity that we need in order for it to be able to dissolve in water. So that one will not be soluble in water. And the last thing we'll look at, and we'll talk about soap here in just a minute, what we notice is that soap has this very highly polar part, sometimes even to the point of being ionic, and a nonpolar part. And we'll look at the structure of that in just a minute and go into a little bit more detail about what it does in water and why soap functions well as soap. How does it really clean your dishes and clothes and things like that? So let's look at a couple more examples down here. Here we have a ketone because our aldehyde or our carbonyl group is on the middle carbon, so we have our ketone there, and having that oxygen in there is actually going to give us some polarity in the molecule. So here we have a non-polar covalent molecule, and we're going to see that yes, this is in fact soluble in water. Here we have cyclohexane, lots of carbons and hydrogens, really not giving us any polarity to this molecule. It has hydrogens, but they don't meet our definition of hydrogen bonding because we have our hydrogens must be attached to a fluorine, oxygen, or nitrogen. So this will not be soluble in water. When we look at something like an alcohol, this is really going to depend on the length of this chain, the length of the carbon chain in the alcohol. And what we find is that smaller alcohols are very soluble in water. So something like methanol or ethanol, very soluble in water. As the chain gets longer, it becomes less and less soluble. And at this point, we have, what, 1, 2, 3, 4, 5, 6, 7, 8. So we have octanol, 8 carbons. This is going to be pretty insoluble in water. So it still has this polar part, but the non-polar part of this molecule is so much bigger that it's going to actually kind of rule what happens with this substance. So when we're looking at smaller things that are just methanol or ethanol, we have this very small polar part, non-polar part, as well as a polar part. They're more balanced out. So the longer the chain, the less soluble something is in water. And I'm not worried about you knowing the exact cutoff. I think in the book they give you some tables that say, well, at 4 carbons or 5 carbons or 6 carbons, it stops being soluble. What I want you to know is that smaller molecules are more soluble in water than larger molecules, and you should be able to rank them in order of increasing solubility in water simply by looking at the size of the molecule, by looking at the length of the chain, as well as looking at the branching. So the same things we talked about with looking at the boiling point of a branch compound, because we were looking at interactions between molecules. The same thing holds true in our solubility. When we start adding branching, we can have a fewer more carbons because that branching is going to limit some of the interactions along the chain of the molecule. So we talked about soaps. We said, well, soaps are kind of different. Here we've got a soap. It's got an ionic head on it. It's got a charged species. Now, there will be a counter ion to that, a sodium or potassium, something in there. But that part is not actually what we're looking at. We're just worried about this carboxylate salt is what we call this. So it looks kind of like a carboxylic acid, but notice it's missing that hydrogen there. So this is a carboxylate salt. And what we see is that we have this very polar end. We got 2 oxygen atoms there, lots of polarity at this end of the molecule, but we also have this very long alkane that is a nonpolar region of this molecule. So the same thing we looked at when we talked about our alcohols, the longer the carbon chain, that the less soluble something was in water. And for most of our soaps, this carbon chain is so long that it's actually not going to be very soluble in water. However, this ionic part of the molecule is very soluble in water. So what we need for soaps is we need this ionic part so that it dissolves in water, and we'll look at kind of how they lay out. But then we also see this nonpolar part because most of the things that we're trying to wash off dishes and clothes are fat-based, are biologically based, and a lot of those things are nonpolar. And so we need something that's nonpolar that we have here with our soap, this big long chain of carbon atoms, all these methyl or carbon groups, and those are the things that are going to interact with the dirt, interacting with all those nonpolar substances on our dishes or in our clothes. And so we kind of have a dual function in the soap. We have the ionic end to make it soluble in water in the first place, the nonpolar end to help us dissolve those fats and oils in our dishes and clothes. So what happens with our water molecule, and a lot of times we don't actually show the all the carbon atoms, we just kind of show this tail on it, because what we're really worried about is what's going on here and that we have this long chain. Soap molecules are very large molecules. And so what happens first is when we're looking at our polar end here, we see that all of these ends, all of these polar ends of the molecules are kind of next to each other, and all of these non-polar parts are here in the middle so that they can kind of keep close to each other. So it's kind of like creating a sphere with all these tails included in the middle of that sphere. Now we're kind of showing a slice of that, but we can imagine this as a three-dimensional sphere with all these non-polar ends together. And so this is what we call the hydrophobic region. So hydro means water. Phobic means fear. So basically these compounds, or these parts of these compounds, have a fear of water, and as a result they're kind of all grouping together here in the middle. And what happens is oil and grease, because it's also nonpolar, doesn't like the water, it actually is attracted into the center of that micelle, in the center of this kind of unit, and as a result, when it goes away, when the water is washed away, the soap is washed away with that water, and as a result it takes that oil and grease with it because it's trapped that oil and grease in the middle of this hydrophobic region. On the outside, where we have these polar regions, these polar parts of the molecule, we call this hydrophilic, and it means hydro, and philic means to love, so it loves water, and that's what we expect to see. So this is the part that's going to be attracted to the water that will help it dissolve in the water, and the hydrophobic part will attack that oil and grease and then carry them away. So we also a lot of times hear things about soap versus detergent, and our little arrow got eaten there in the translation. And so soap is synthesized from natural triglycerides. And so that means they take natural products and they create soap. We tend to use soap and detergent interchangeably, but they're really not. So soap is actually synthesized from natural products. And we know that the sodium and potassium salts are very soluble in water. However, we also get some magnesium and calcium salts, especially in Kentucky where we have very hard water. There's a lot of magnesium and calcium in the water, particularly the calcium carbonate because of all the limestone in the earth here in this part of the country. And so what we end up with is magnesium and calcium in the soap. They don't dissolve very well, and so what we end up with is soap scum. We end up with rings around the tub, so those are actually those soap molecules, and they've been attached to a magnesium or calcium, and so they don't dissolve quite as well in water as the other salts do. And so soaps are used a little bit differently. When we look at something like a detergent, we want to make sure we don't end up with soap scum in our washing machine, but we also don't want to end up with soap scum in our clothes. So we want something that is a little more soluble in water, more readily soluble in water. And so detergents are actually synthesized from petrochemicals, which just means they're oil-based chemicals. As we refine oil, we get a lot of things out of it that are used in other ways. So refining oil just doesn't give us gasoline. We actually produce a lot of other things from that as well. And so these salts are much more soluble in water, and so as a result, we get no soap scum. So we don't get the soap scum in our clothes or in our washing machine. So that ends this unit on solubility. We'll talk a little bit more about solubility in some later chapters about how much will dissolve and things like that. Right now we're just worried about looking at the intermolecular forces and how those intermolecular forces interact and how they affect the solubility. The golden rule of solubility is like dissolves like. Things with similar intermolecular forces will dissolve in one another. Things with unsimilar or dissimilar intermolecular forces will not dissolve.